Hi, my name is Ingo. Today I'm going to present work on evaluating query languages and systems for high-energy physics data. The work was accepted just a couple of weeks at PVLDB and is a collaboration of a couple of people from this group, Dan, me, Ghislain, and Gustavo, as well as two particle physicists at the University of Washington, Mason Proffitt and Gordon Watts. In short, what we do in this work is to implement physics queries in a number of general purpose query languages and compare their suitability and contrast that with the domain specific tools that the physicists use today. For us, the main motivation is to understand what are the limitations of these general purpose systems in order to derive research items from them. But it also, and it seems like there are quite a number of them, but it also turns out that this was interesting to the physicists and in particular the developers of the domain-specific tools that are used today. And they found some of the features of these general purpose systems quite interesting. We talked to them 2 weeks ago and have potential follow-up work. Before I start, let me tell you that you can interrupt me at any point in time. I'm happy to do the discussion in line with the presentation. So to start, let me give you a brief background on high-energy physics. In very short, they have this huge machine that produces huge amounts of data. More concretely, what they are doing with this machine is that they accelerate particles at a very high speed and then intersect two beams at a particular frequency in the order of 40 million times per second. And every time these two beams intersect, that thing is called an event. And each event, for each event, then they register what kind of other particles have been created that were detected by some sensors. Inside of the sensors, there's a cascade of filters. So out of these 40 million events per second, only 1,000 events per second approximately is interesting and then archived on disk. And even that small fraction already represents a humongous amount of data, as many as 88 petabytes in the year 2018, I think, with exponentially growing numbers every year. And then what they do with these large amounts of data is to analyze them, is to share them around the world and analyze them in various groups around the world. An analysis usually produces a plot, as you see here on the right, and involves maybe data in the order of some gigabytes to some terabytes. The outcome of an analysis is usually a plot like this one, where and the plots are really histograms where a specific subset of these events is considered interesting. And then for the interesting events, the physicists derive some measures of the events and plot a histogram of these measures. And while I'm able to do this very high level summary, I have fundamentally no idea what the machine does. And I have no real idea how to interpret the analyses that they do. And what we do know is that this analysis itself is something that we are familiar with. As database people, we have seen this from many different domains, people who look at data and try to derive insights. So our first reflex after getting the first contact with high-energy physics was to think, why don't the physicists not use the general purpose database systems that we in our community are so proud of building? And at the first sight, it seems like a really great fit. If we look at the requirements that high-energy physics have, they seem to fit what database systems do. The data is always fully structured, so we can, in principle, store the data in the relations that we are familiar with for the last 40 or 50 years. Admittedly, they have quite a large scale, but we have also developed techniques in order to handle large amounts of data. In fact, they have read-only data, which is a rather easy case, and we have read-optimized systems that exploit some of that have optimizations for this specific case. And they want interactive analysis, but we have also tools such as query languages and intuitive user APIs that should make that possible. Now, what is the one feature that isn't a great fit is the fact that data is nested. I told you earlier that what they register is a number of particles for each event, and the analysis are really also centered around the concept of an event. So the way how physicists store the data is in the form of nested data, namely the particles per event, and then they express the computations as nested queries per event as well. And now the textbook's approach for this kind of data would be to normalize the data and have one relation for each particle type, and then join these relations in order to produce the final results. The physicists have looked at this approach and rejected it because this is not only a runtime overhead, but in particular a mental overhead of these joins. The thing is that database systems have evolved, and modern SQL don't have these limitations anymore. In particular, with the SQL 99 standard, there are now structured types in forms of records and arrays, and there's a support for nested subqueries that allow to express, in this case, per event computations relatively intuitively. So in this work, we wanted to review this decision of whether general purpose query languages are a good fit. And we more concretely, we compared several existing languages and systems for this specific use case. For that, we tried to answer a couple of very concrete research questions. The first is, what are even the language features that are required for high energy physics analyses in the first place? And then in the context of our comparison, how well do the different languages or APIs support the features that we identified previously? And apart from supporting them at all, we also wanted to understand how the underlying systems deal with the data sizes and how efficient they are. In order to answer these questions, we took a benchmark that the physicists that also co-authors of the paper have developed in the past, with the goal to show representative queries of that domain. And we extracted 16 different query patterns and classified them by importance. We implemented the full benchmark in 4 different SQL dialects and 2 additional NoSQL languages, and compared the resulting implementations with the domain-specific tool from the root framework, data frames. And finally, we run all of the implementations on various orders of magnitude of the data set, and as well as different amounts of resources. In the end, I already said it in the very beginning, in the end, what we want to achieve with this work is to understand the weaknesses in the current system in order to derive research items that we can work on in the future. As a sneak preview to the result, the query languages that we have studied have somewhere between reasonable and excellent support for expressing high energy physics queries. However, they currently significantly lack performance. So let me start with the first 2 research questions. What are the language features and how do the different languages support them? As a disclaimer, these questions, as you may imagine, don't have objective quantitative answers. So, the problem being that how well or how important a language feature is and how well it is implemented first can't be determined in a very objective way. And it also depends on the specific taste of a programmer, experience, and background, and maybe just opinion. So what we're doing in this work is to study a couple of patterns, and I will show them a number of them to you in this presentation, such that everybody can form their own opinion. Let me start with some preliminary and talk a bit more about the data model and how the different systems expose them to their users. The mental data model that physicists have in mind is shown on the right. There are a number of quantities that are really structures. For example, there's this missing energy that has a number of floating point dimensions, and then there are particle types such as muons, which also have a number of dimensions. And each event really consists of either a single of these structured quantities like the missing energy, or a variable number of these quantities such as particles. And now what is very important to understand is that there is this strong ownership relationship between particles and events, meaning that a particular particle that is part of an event is only part of this event and does not make sense to be looked at outside of this event. So the mental model is really centered around an event which has some internal structure. And then in order to analyze the one entire experiment, there's a large number of these events over which we want to, which somehow we want to summarize in the end. What is important to take away here is that there's this intrinsically nested data model that is part of this that represents this use case. Now, if we look at how the root framework and our data frames consequently represent this data, at least in the nano AOD format, which is one format that root understands, the representation is the following. There's events are called in a so-called tree, which you can simply think of a relation, which consists of branches, which is in a way another form of word for columns, which contains just scalars. As an example, we have the tree or relation called events with branches or columns called MET_PT and similar that represent the different dimensions of the different structured quantities that you saw on the right. So what you see here is that the nano AOD format of root exposes the data as a columnar data model, and the underlying reason, among others, is to reduce the I/O. Many times the query is only interested in a subset of the dimensions, in particular maybe a subset of the particle types, and storing data in a columnar way allows to read only the columns that the query is interested in a row-based format that wouldn't be possible. Now, what is interesting and important to understand is that there is a mismatch between the mental data model that users have in mind and the physical data model that data is stored in and also exposed to the user. Now, because the root format isn't supported by any of the general purpose systems that we studied, we converted our data into Parquet, and we also slightly changed the data model that it exposes. In Parquet, data is stored in tables, but these tables may have nested types. So what we can do here is to store several attributes as one struct, which gives us a single struct valued column. And the same thing for particles. Here we have the muon column that has the type list of struct of a number of dimensions. And the obvious advantage is that we fit the mental data model better, but behind the scenes, this is still decomposed into columns. So we still get the benefit of I/O efficiency. The reason or the underlying concept why this is possible is really data independence. In database systems, that's a common thing to do, to separate the logical and the physical data model, and therefore get the best of both worlds. So somewhat keep in mind the data model. We will need it when we now start understanding the different query patterns. And I will start with one that is quite related to the data model, namely patterns for accessing and creating structs. What I typically do is to show a pattern in the R data frame interface, which is the one that physicists use today. And the interface is really typical data frame interface, as you may know from Spark or other similar systems, where you can define these chain of transformations before eventually the whole chain is executed. What we are doing here is to define a new dimension or column called jet_p4 that is produced by a user-defined function, and to whom we give the input as an input for different existing columns. What you can see here is that the columns, the scalar columns that were initially present in the input are exposed through their individual names. And the reason why this user-defined function is necessary is because our data frame doesn't understand the concept of structs at all. The only way to produce structs is through some user-defined type that is returned here by the make_p4 function, which is completely opaque to our data frames. That's different in all of the other dialects, which have some support for records or structs. Here in BigQuery, we're using the constructor called struct in order to create a new record. And in this case, we're creating a record where the first field is called X and the second field doesn't have a name. You can also see that accessing a member happens with the normal, works with the normal dot notation. In JSONic, the construct is very similar, though with a different syntax. We specify the member names with strings similar to the JSON data format, but then we can use arbitrary expressions in order to compute values. In SQL++, that's one of the the other NoSQL language in the study. The same syntax is also possible, but there's an additional one. We can use here a nested query, and on the outer context, the records from this inner relation are equivalent to structs. So there's only one concept for rows in a relation, and structs, it's in fact the same concept. Bottom line is that the constructs, both for creating and accessing structs, should be very similar to other programming languages and therefore familiar to most programmers. What is maybe a bit more specific is how arrays are accessed. And what I'm showing here is an example from the R data frame interface that uses columnar operations. If you remember, we have a variable number of jets, that's just one particle type per event. So this here is one dimension of all of the particles of this event. So this is an array of scalars. So the comparison that is done here has actually element-wise semantics. What we're getting back from this whole expression is a vector of Booleans, which we can then reinterpret, sum up, and therefore get the number of jets that qualify for this condition. And these columnar operations are really a consequence of the fact that data is stored and exposed in columnar way to the user. For the SQL dialects, that's different, and I'm showing here an example that works both in BigQuery and in Postgres. In BigQuery, we run these nested queries, which roughly have the semantics of running once per outer row. So this inner query is run for every outer row, where for each individual execution, this thing can be thought of as a constant input. So there's this jets array valued column called jets, which we can use as an input for this inner query. And what SQL allows us to do through the unnest function is to treat this array as a relation and then use it in a from clause as we would use any other relation. So what this does is to select the different records from this array, bind them to the variable name j, have some filters on every j, and then compute an aggregation. So this works rather nicely. Let me contrast to you what happens if we don't have these nested queries. I'm showing here a query that can either run in Presto or Athena that doesn't support, both of which don't support these nested queries. And what we have to do instead is to use this cross-join construct also with an unnested, with an unnesting of this array. And the semantics here are a bit more obscure. The semantics are to flatten each of these arrays and duplicate for every outer level row all of the other attributes. As a consequence, we can still filter by one of the attributes of j. However, to if eventually we want to access something, an attribute that wasn't part of J, we need to undo the flattening, and we do that by grouping. If you don't fully understand what this query does, you've actually understood the main point. It's rather difficult to understand. In contrast, in JSONic, we also have these nested queries. In a way, we also have columnar expressions where here instead of unnesting, we use this empty brackets operator in order to unnest the array elements, and then we can apply this element-wise filter on them. What is important is that this inner expression is run once per outer row, so we also have the possibility to nest expressions in a rather intuitive way. Our takeaway for this, and again, and to some degree, this is opinionated, is that these nested subqueries can be rather elegant, and we would go as far as to say that they are necessary. SQL without these nested expressions or queries is rather cumbersome. Then let's move on to a different way of using arrays, which is very common in high-energy physics. Instead of producing combinations of particles, what this example here does is to produce any pair. That's why we have two here. Any pair of jets, and in particular, this doesn't include duplicates. So for two different jets A and B, we only want AB or BA, but not both. And because this is so common, the physicists have a built-in function called combinations. In BigQuery and many other SQL dialects, we can reconstruct the same functionality with what we have seen earlier already. So we can access with the unnest function the arrays as if they were tables, and then bind the index of each element in the array to a variable, here I and j, which we can use to filter out duplicates. With Presto, that doesn't have nested queries. Again, we need to have a top-level query and use the cross-join construct, which is somewhat more cumbersome. So the difference actually remain. The two systems differ in the same point as previously. One supports subqueries and the other one doesn't. And then there's another small difference, which in this dialect, for some obscure reason, we must spell out the different fields, which not only make the query longer, it also becomes more tied to the specific input data than necessary. And then in JSONic, we have a similar construct as in BigQuery, except with a different syntax. We have what looks like two nested for loops, where we can also, again, bind indices to a variable and then use that variable to filter out duplicates. In short, in many of the query languages that we studied, we can produce these combinations with basic constructs, which maybe has the benefit that we can immediately see what this construct does. Now let me move on to a different type of pattern. Until now, in a way, I've showed you individual steps of a computation. Let me now move on to how to assemble larger computations and study patterns for chaining different steps. As you may imagine, that data frame interface of the root framework allows to chain transformations simply by writing them one after each other, separated by a dot. So here, for example, we have an initial filter, then we define additional quantities, we can filter again, define more quantities, etc. In SQL, and I'll show an example of BigQuery here, this isn't as easy. We can't add columns to a relation and use them inside of the same relation. What we have to resort to instead is what I call poor man's variables, which have to be relation valued. So we can define, with using the with clause, a relation called a relation that only exists in the scope of this query called leptons, of which we provide a definition, and then in some next relation use it as an input. And this way we can chain the computation of different relations. The reason why I'm calling these poor man's variables is that in fact it involves a nesting level that we aren't interested in at all. What we may want is to define a variable within each event, for example, containing a new particle type that we have detected. But we can't store variables per event. We can't store variables at that inner level. We need to go through this outer level in order to achieve something close to variables. So in SQL, we need to switch between this inner and outer level, which in fact isn't necessary intrinsically in our computations. In the NoSQL languages, and I'm just taking JSONic here as an example, the designers have understood this problem, and they allow almost real variables. So what we're looking at here seems to be a for loop where we bind value, or where we seem to assign values to variables that really have a scope just within one event. So they do encapsulate the computations that are natural in this use case. I'm still calling these, I'm not calling that, they aren't really variables, they are rather value bindings. They aren't variables because they don't keep state. In a way, they are single static assignment variables that really only bind values, and that has a benefit of how many optimizations can be done by a query optimizer. So in short, the lack of variables in SQL is really cumbersome, but the NoSQL languages that were designed with this drawback in mind have understood that and give reasonable constructs to programmers for our use case. Let me move to the final pattern, that of defining and using functions. We've seen this example earlier where we have that make P4 function that we can use in this way. And really what the root framework allows is to use arbitrary C++ functions. So this gives a partial definition of that function that we are using. And you see that, of course, apart from being powerful, this design decision also has some of the disadvantages that C++ has, namely rather verbose syntax, where we have to explicitly define return types and variable and parameter types, and maybe the general difficulty of using such a powerful language, in particular for novice programmers. One other thing that really makes this approach powerful, though, is the fact that the root library functions are all available in these queries, and they encapsulate not only some vector-related functions, but in particular a huge body of physics-related functions that you definitely don't want to repeat in every single query. Let's see how the SQL-based systems do that. I'm taking the example of Postgres, and in particular, what I find interesting here is that all of the systems support one way or the other to have generic arguments. So we can, with a single implementation, define all overloads of a function where the function body makes sense for all input types where the function body makes sense. And then the function call, you see it here, is exactly as you know it from almost all other languages. The same thing is true in JSONic, and again, the difference is mostly in syntax. Here in JSONic, if you don't want to specify a type, you don't even need to write any element or anything. You just don't write any type. So what our opinion about these patterns is that the generic functions in SQL and NoSQL are very concise. However, from the SQL dialects, there are also a number of limitations that you can't really see in patterns. Maybe the most prominent one is that none of the SQL dialects allows to define functions that take relations as an input or produce relations. So there is some limitation of what you can encapsulate in functions and what you can't. Okay, so let me summarize what I've presented so far. We have seen a number of these patterns, actually all of those that you see here, are nesting arrays, producing combinations, and defining user-defined functions. And we did a best effort to quantify how the different systems implement those. There are a number of patterns that you've also seen, how to access and create structure types, how to express subqueries and variables, as well as a number of more patterns, which we think are still relatively important, but not as fundamental as the previous category. And then there's yet another category of patterns which are somehow useful syntactic sugar, but without which query languages can still do a decent job in expressing high energy physics queries. Our takeaway from, or some high-level observations from this attempt to quantify things is that in general, the query languages support all of the essential features. So in principle, they are all a viable way to express queries in high energy physics. However, we also see differences, and some of them are really in the details, but they still may make a significant difference. Some of the constructs are still quite cumbersome, depending on the dialect. Overall, our impression is that the NoSQL languages seem the most elegant, and in a way this isn't surprising. They have been built in order to analyze documents, and documents really consist of nested and heterogeneous data, which is a superset of nested and homogeneous data that we've seen in this domain. And I think that was interesting for the physicists. We do see a potential for improving our data frames. Some of the constructs from the NoSQL languages do seem more elegant, at least to us, than the constructs that our data frames have today. In short, the SQL 99 standard, as well as the NoSQL languages, in our opinion, are at least in principle suited for high energy physics analysis. Now let me move on to the second part, where we study how scalable and efficient underlying systems are. You see here a link where we release the full code. We have run everything in the cloud and in the public cloud, and we have released the scripts all of the scripts that are required to run our experiments. So in principle, it should be rather straightforward to reproduce exactly the numbers that we have also in our paper. So let me first show you an experiment where we study how efficient and scalable the systems are with respect to the machine size. We're using here a relatively small data set, 53 million events or 17 gigabytes. And we're using different instances on AWS, namely from the M5 instance type, and we vary which instance size we're using. So we are varying from 1, which is the smallest instance size, up to 48, which is the largest one. All of the other resources, such as disk and network, but also the price, are proportional with the number of cores. So what we will get for the different systems is a curve like this. I'm showing here the one for our data frames, where the top most data point is usually the one with a single core. And what we are plotting for each data point is how long the query is running. And here on a single core, we're running a bit less than a minute, and how much renting the resources for running just this query takes, 0.1 cent in this case. And then as we add resources, as we increase the number of cores, what we expect is more or less happening here, namely the running time decreases. And because we are still renting, because we are renting for roughly linearly lesser time, because scalability is close to linear, the running time is decreased roughly by the same factor as we increase the resources. So overall, the product, which determines the price that we're paying to the cloud provider, remains. So this explains why running time goes down, but price doesn't go up significantly. This is only the case as long as scalability is linear or close to it. And then you see that we reach some scalability limit where increasing more resources doesn't lower running time, but because the renting time increases, also the overall price increases. Note though that for this system, this only happens in the order of 2 or 3 seconds. So the system is still really good in providing interactive analytics. Let's start with the first general purpose system, Presto. This is the fastest on-premise system that we have. The shape of the curve is similar for exactly the same reason. However, there is at least half an order of magnitude in difference in both running time, and therefore, because we're paying per renting time, the cost is also increased by roughly the same factor. If we now add the two NoSQL systems, DB and RumbleDB, that's our implementation of JSONic, we see that both running time and therefore the cost have increased again by at least half an order of magnitude. Our system is actually the slowest. We have between 1.5 and 2 orders of magnitude of difference in both running time and price. So while these two systems fared best in, or at least arguably best in how well they can express the queries, they are so slow and expensive that for many cases they aren't practical. Postgres, which you could think is the most mature system among the SQL-based system that we have studied, actually performs at least as bad as these JSON document stores or NoSQL systems. You see by this horizontal line that for this query, Postgres isn't even able to execute the query in parallel. So what's happening here is that we have the single core running time here, and then we add resources that aren't used. So the running time isn't decreased, but the renting price increases with the additional resources. And in fact, the system isn't able to parallelize any of the queries except query 1, which is really the most trivial one. And then let me add one more class of systems, which are those two different query as a service systems from two of the main cloud providers. Let me start here with BigQuery. BigQuery is among the fastest system. In many queries, it's on par and sometimes even better in terms of running time than our data frames. However, because we are paying per query and supposedly the cloud provider cross-finances the queries or just adds a particular margin to the price, what we are paying per query is about an order of magnitude higher than what we would do in our self-hosted solution. The real comparison is a bit more complicated. It could be that we are underutilizing our resources and that there's large idle time between two subsequent queries. In these cases, the cloud-based systems could be also more cost efficient, but I don't want to go into too many details in this discussion. What I think is interesting is that BigQuery was one of the systems that was both one of the most expressive ones, and it's clearly one of the fastest ones, one of the two fastest ones. So there is a general purpose system that is both efficient, scalable, and expressive, which gives all of the other systems hope to improve in the dimensions where they are currently not faring great. I've shown you here the picture of query 5, but we actually run this for all of the other queries in the benchmark as well. There are 8 of them, and the picture is very similar. The only difference here is that for query 1, Postgres is able to parallelize as the only query, and then maybe there's a specific thing to be said about query 6, which is really compute intensive. And this is the only query where the cloud-based systems are actually cheaper than all of the other systems. And the reason is due to their pricing model, where computations are free and we only pay for the amount of data in the input. The high-level takeaway is that the general purpose systems maybe with the exception of BigQuery, are not optimized for high energy physics, and BigQuery, in contrast to the others, is relatively expensive. We also studied how scalable the systems are with respect to large data sets, and I don't want to go into too much details. What you see on the right side, of every plot, is that as the data increases, running time increases roughly linear. This is a log-log plot, so the linear line here is actually a linear relationship between the input size and the running time. And this in turn means that the data set size alone doesn't seem to be a challenge. Adding more data just takes linearly longer time, but not more. So let me summarize what I've presented you today. We presented in this work, we compared in this work a number of existing languages and systems in the context of high energy physics. And we wanted to understand what are the language features that are required in this domain. And concretely, we extracted a number of patterns from an existing benchmark and classified them by performance, as well as try to quantify how the different systems implement them. We compared the different query implementations across the different systems. Namely, we had 4 different SQL dialects in the comparison, 2 additional NoSQL languages, and the state-of-the-art that physicists use, the R data frame interface. We implemented the benchmark and run them across a variety of variables in order to understand how scalable and efficient the underlying systems are. In the end, we think that we could derive quite a number of weaknesses in the systems. Most notably, there are some details in what exact features the query languages support, but then maybe the biggest takeaway is that performance isn't where it should be. In one sentence, I think the summary of this work is that the general purpose query languages have somewhere between a reasonable and excellent support for high energy physics, but currently they lack performance by a large margin. That finishes my presentation, and now I'd be happy to answer any questions that you may have.